In the past couple of videos, we've taken a look at this fundamental theorem of calculus part 1. And remember that really all this is telling us is a derivative rule, our final derivative rule of Calc 1. And it's a little bit of a complicated derivative rule because it's actually one of the only derivative rules we have that comes with a condition. It has the condition that this function on the inside of the integral first had to be continuous on the interval from a to b. And then I could see that the derivative rule was that the derivative of this integral function would just be that, or kind of imagining following the process again of taking that upper bound, dropping it in place of the value of t, and then getting rid of the integral symbol and getting rid of the dt, and just being left with that f of x. So that's kind of at least the visual that I'm imagining every time I do an example of something like this where I use this derivative rule. So let's take a look at how we would apply this to several examples here in this video. And we'll be able to move through a lot of these very, very quickly. So let's take a look here. Here's a function g of x, and notice it's defined by a weird integral function. If I plug in a value for x, it goes in place of this x in the upper bound. So the first thing I would need to do to find the first derivative is ensure that this function here is indeed continuous on the given interval. So I'll say here that since my f of t in this case is a square root of 1 plus a t squared, and is that a continuous function? Well, I mean, there's nothing I can plug in to make the inside of the square root go negative, so yeah, this is definitely going to be continuous on the interval from 0 to x, really for any value of x. It doesn't really matter what the value of x is. And so I can say then by the fundamental theorem of calculus part 1, or as I'll abbreviate it, fundamental theorem of calculus part 1, FTCP1. It's fun to say. I know then by this that I can easily calculate my derivative by saying I'm going to take the function, take that upper bound of x, drop it in place of the t, and then erase the integral sign, erase the dt, and boom, I have an answer. Like, that's actually one of the easiest derivative rules we have, and that's it. Example number 1 is complete. I just have to make sure that I check this appropriate condition. Let's take a look now here at example number 2. I want to find the first derivative of the function, g of x equals, and I have another thing like this. Now, one thing that I'm going to notice right away on this function is that this doesn't quite fit the form for the derivative rule that I saw in the box up above. Notice that this derivative rule had a number as the lower bound and x as the upper bound. And so if I want to use this derivative rule, I have to make sure I have my integral set up in that order first. So here on number 2, I'm going to go ahead and just quickly note that if g of x is going to be equal to an integral from x to 10, then certainly I could rewrite that as negative of the integral from 10 to x. Oops. And then if I wanted to, I could even go ahead and bring that negative, since it's a constant, and multiply it to the inside of the integral. And I could rewrite this, just to make it really simple, as an integral from 10 to x. And then notice e to the t minus t would be the result of the inside after I multiply by a negative. So now I'm going to use this form of g of x to take the derivative with. But before I do that, I need to check my appropriate condition. So let's see. I'll say since f of t equals e to the t minus t, and notice that's always a continuous function. That's exponential minus a polynomial. There's no issue here. I can say this is continuous on the interval from 10 to x for any x value, then by the fundamental theorem of calculus part 1, I can calculate that g prime of x is going to be, and again, it's super easy. I just take my f of t formula, I write it down, but replace all the t's with the upper bound of x, and then erase the integral sign, erase the dt, and boom, you have an answer. That's it. We're done. All right, let's try a couple more of these. These are really, really simple. Let's try example number 3. Now this one here is a little bit strange to try to work with, but it's not too bad. Notice here I have a function k of x. I want its derivative. And okay, I see that I have 1, and I have my variable up in the upper bound, so that's good. I don't have to kind of reorder anything. And now I have this sine of t over t as the inner function. Okay, so I'll start here and say, since the sine of t over t, oops, I guess I should say since f of t is equal to the sine of t over t. And this function here is definitely going to be continuous on the interval from 1 to x to the 4th. I probably just have to be a little careful here. I need to make sure that x doesn't ever turn into, or my interval doesn't ever pass through the value of 0, right? Because if it passes through 0, that would be a really, really, really big problem. So I would say that this works here for any x that is greater than 0, right? Like I don't want to use anything that's going to be less than 0, because then I would go from 1 and start dealing with some messy numbers. I want to make sure I don't use the value of 0 here. So I'll go ahead and start to take a look here at how I can use the fundamental theorem of calculus, part 1. So I'll say then, by the fundamental theorem of calculus part 1, we'll go ahead and start to use the rule. So again, I remind myself of what the rule actually looks like. Oops, sorry, this isn't a g, this is a value of, or a function labeled k. So my k prime would be, all right, so I'm going to take this upper bound and I'm going to drop it in place of all of the t's. Okay, so that's going to look like this. And then I erase the integral symbol and I erase the dt, and I should be done, right? Actually, I got to be a little careful here. You probably already spotted that there's an issue, because in all of the previous questions, and actually in the theorem itself, was the upper bound allowed to be x to the 4th? No, I mean, the upper bound had to be x. If I go all the way back and I look again, the upper bound just has to be x. It doesn't say it can be sine of x or x to the 4th or x squared or x plus 2. It says it should be x. So I got a slight problem here. I have a derivative rule that only uses x, but now it looks like instead of having x, I have x to the 4th plugged in. What you can kind of see is that this will almost be similar to like if I had a function, k of x, that had a sign of, say, x to the 4th power in it. I could think about taking the derivative by using my rule for the derivative of the sine function and just kind of ignore the fact that the x to the 4th is there. But of course that would be incorrect. We know that when I have something more complicated plugged in than just an x, I'm forced to follow up with just a chain rule. And so I'll notice here that since I have something more complicated than just an x plugged in, I'm going to be forced to follow up with a chain rule. So I'm going to have to say this is the derivative of the integral function thing. The upper bound drops in, I erase the integral sign, erase the dt. But then I look at the upper bound, I look at the stuff, and is it just an x? No. So I have to follow up with a chain rule. Now, of course, here, this would allow me to go ahead and simplify this down a little bit, and I could end up with, let's see, I guess a 4 on top and just an extra x on the bottom. I could cancel some of those x's. So I do have to be aware here that the chain rule might be able to come into play with this derivative rule. And because of that, I just have to note that whenever this upper bound is not just an x, but more complicated, then I apply the chain rule, just like I would have with any other derivative rule. So let's take a look here at something like example 4, and we can see the exact same thing coming into play. Notice here my upper bound is a bit more complicated than just x, so I know I'll need a chain rule. I'll start though by seeing that in this case I have an f of z is equal to a z squared over z to the 4th plus 1. And clearly that's always going to be continuous. The denominator can never turn into 0. So this is going to be like continuous on here, and this is of course for all values of x greater than or equal to 0. Of course, I don't want to plug in negative x's because then I'm going to get square roots of negatives. But definitely, no matter what I plug in otherwise, this function will always be continuous on that interval. So I can say that by the fundamental theorem of calculus part 1, I can arrive at the following derivative. I'm going to take my upper bound. I'm going to replace all of my z's with it. Oops, that should be a fourth power. And then I look at the upper bound. Was it just an x? No, it was not. So I have to follow up with a chain rule, which would be 1 over 2 square root x, the derivative of that radical. So of course, if I was to simplify this up a little bit, you can see that I'm going to end up here with just my value of x, my value of x squared plus 1 in the denominator, and then if I wanted to, I could multiply that 2 over root x down there as well. So hopefully this gives you a sense of how I can use this new derivative rule. It's not really that hard of a derivative rule, but it is obscure, and it probably takes a little bit of practice just to get used to. You got to just get the weirdness out of the system at the start. Now in the videos to come, we'll start to see why exactly we really care about this derivative rule. Like, it's interesting that we have this new function and that we found a way to take its derivative, but what does this have to do with the big question that we've been asking for the past several sections, which is, how do I calculate big complicated areas under curves when I have these really complicated definite integrals? How does the fundamental theorem of calculus part 1 help make the evaluation of those complicated integrals a bit easier?